Welcome to our deep dive into the fascinating world of current electricity. In this chapter, we'll explore the fundamental concepts that govern the flow of electric charge in materials, understand the laws that describe their behavior, and derive important relationships that form the backbone of electrical circuits. Whether you're a student preparing for exams or just curious about how electricity works, this video will guide you step by step through definitions, derivations, and practical applications. Let's begin our journey by understanding what electric current really means and why it's so crucial in the study of physics and engineering. Electric current is one of the most basic yet essential concepts in electricity. It refers to the rate at which electric charge flows through a conductor. Imagine a wire with charges moving through it. The amount of charge passing through a cross-section per unit time is called the electric current. It's measured in amperes, where 1 ampere equals 1 coulomb of charge passing per second. Understanding current is fundamental, as it forms the basis for analyzing all electrical circuits and devices. Next, let's look at what causes these charges to move inside a conductor. Drift velocity is a key concept that helps us understand how electric current actually flows in a conductor. When an electric field is applied, free electrons in the conductor start moving with a small average velocity opposite to the field direction. This average velocity is called drift velocity. Although electrons move randomly due to thermal energy, the electric field gives them a net direction. Drift velocity is usually very small, but it's crucial in determining the current in a wire. Now, let's see how drift velocity relates to electric current mathematically. Relationship between electric current and drift velocity is fundamental in understanding how conductors work. The current I in a conductor can be expressed as I equals N of A, where N is the number density of charge carriers, A is the cross-sectional area, V is the drift velocity, and E is the charge of an electron. This equation shows that current is directly proportional to drift velocity. If the drift velocity increases, so does the current, provided other factors remain constant. This derivation forms the basis for analyzing current at the microscopic level. Mobility is another important property of charge carriers in a conductor. It refers to how easily these carriers, like electrons, can move through the material when an electric field is applied. Mathematically, mobility is defined as the drift velocity per unit electric field. Higher mobility means that charge carriers can move faster, resulting in higher current for the same electric field. Mobility depends on the material and temperature, and it plays a crucial role in the conductivity of materials. Next, let's discuss a fundamental law that governs current flow: Ohm's law. Ohm's law is a cornerstone of electrical science. It states that the current flowing through a conductor between 2 points is directly proportional to the voltage across the 2 points, provided the temperature remains constant. This relationship is expressed as V equals IR, where V is voltage, I is current, and R is resistance. Ohm's law helps us predict how circuits behave and is widely used in designing electrical systems. Now, let's derive the microscopic form of Ohm's law to see what happens at the atomic level. The microscopic form of Ohm's law connects the macroscopic behavior of circuits with the microscopic properties of materials. It relates the current density J to the electric field E using the equation J equals sigma E, where sigma is the conductivity. This form shows that the current density is proportional to the electric field, and the proportionality constant is the material's conductivity. This perspective helps us understand how material properties influence current flow at the atomic scale. Next, let's define electrical resistivity and see how it fits into this picture. Electrical resistivity is a property that quantifies how strongly a material opposes the flow of electric current. It is the reciprocal of conductivity and is denoted by the symbol ρ. Materials with high resistivity, like rubber, do not allow current to pass easily, while those with low resistivity, like copper, are excellent conductors. Resistivity depends on the material and its temperature. Understanding resistivity is crucial for selecting materials for wires and components in electrical circuits. Now, let's look at conductivity, the flip side of resistivity. Conductivity is a measure of a material's ability to allow the flow of electric current. It is the reciprocal of resistivity and is denoted by the symbol sigma. Materials with high conductivity, such as metals, are used extensively in electrical wiring and circuits. Conductivity depends on the type of material and its temperature. The higher the conductivity, the easier it is for current to flow. This property is vital in choosing materials for efficient energy transmission. Next, let's discuss how temperature affects resistivity. Resistivity of most materials changes with temperature. For conductors, resistivity increases as temperature rises because atoms vibrate more and scatter electrons more frequently. In contrast, for semiconductors, resistivity decreases with increasing temperature as more charge carriers become available. This temperature dependence is crucial in designing circuits that operate reliably under different conditions. Understanding this concept helps engineers select the right materials for specific applications. Now, let's move on to how resistors combine in circuits, starting with resistance in series. When resistors are connected end-to-end in a circuit, they are said to be in series. In this arrangement, the total resistance is simply the sum of the individual resistances. This is because the current has only one path to follow, and it encounters each resistor one after the other. The formula is R total equals R1 plus R2 plus Rn. Series connections are common in many electronic devices, and understanding them is essential for circuit analysis. Next, let's see what happens when resistors are connected in parallel. In a parallel arrangement, resistors are connected across the same 2 points, providing multiple paths for current to flow. The total resistance in parallel is always less than the smallest individual resistance. The formula is 1R total equals 1R1 plus 1R2 plus 1/Rn. This setup is used when you want to decrease the overall resistance and allow more current to flow. Understanding parallel connections is vital for designing efficient electrical networks. Now, let's derive the expressions for equivalent resistance in both series and parallel. Let's derive the expression for equivalent resistance when resistors are connected in series. Since the current is the same through each resistor, and the total voltage is the sum of voltages across each, we get R total equals R1 plus R2 plus Rn. This simple addition makes calculations straightforward for series circuits. Knowing how to find equivalent resistance helps in analyzing and designing circuits efficiently. Next, we'll derive the expression for equivalent resistance in parallel connections. Resistors in parallel, the voltage across each is the same, but the current divides among them. The total current is the sum of the currents through each resistor. Using Ohm's law, we derive 1R total equals 1R1 plus 1R2 plus 1/Rn. This formula allows us to calculate the overall resistance in parallel circuits, which is always less than any individual resistor. Mastering this derivation is key for circuit analysis. Now, let's introduce Kirchhoff's laws, which help analyze complex circuits. Kirchhoff's laws are powerful tools for analyzing electrical circuits. There are 2 laws. Kirchhoff's current law, KCL, states that the total current entering a junction equals the total current leaving it. Kirchhoff's voltage law, KVL, states that the sum of the potential differences around any closed loop is 0. These laws are essential for solving circuits with multiple loops and junctions, where simple series and parallel rules are not enough. Next, let's see how to apply these laws to solve a circuit. Solve a circuit using Kirchhoff's laws. Start by labeling all currents and assigning loop directions. Apply KCL at each junction to set up equations for current, and use KVL for each loop to relate voltages and resistances. Solve the resulting system of equations to find unknown currents and voltages. This method is especially useful for circuits that cannot be simplified into series or parallel combinations. Now, let's explore special circuit arrangements like the Wheatstone bridge. Wheatstone bridge is a special circuit used to measure unknown resistances accurately. It consists of 4 resistors arranged in a diamond shape, with a galvanometer connected between 2 opposite points. When the bridge is balanced, no current flows through the galvanometer, and the ratio of resistances can be used to find the unknown value. The Wheatstone bridge is widely used in laboratories and sensor applications. Next, let's derive the condition for a balanced Wheatstone bridge. Wheatstone bridge to be balanced, the ratio of the 2 pairs of resistors must be equal. Mathematically, this means R1, R2 equals R3, R4. When this condition is met, the potential difference across the galvanometer is 0, and no current flows through it. This balance condition allows for precise measurement of unknown resistances by adjusting the known resistors until the galvanometer reads 0. Now, let's look at a practical application of the Wheatstone bridge, the meter bridge. Meter bridge is a practical device based on the Wheatstone bridge principle. It consists of a 1-meter-long wire stretched over a scale, with known and unknown resistors connected in the bridge arms. By sliding a jockey along the wire, you can find the balance point where the galvanometer shows 0 current. The meter bridge is commonly used in physics labs to measure unknown resistances with high accuracy. Next, let's discuss another important instrument, the potentiometer. Potentiometer is a device used to measure the EMF of a cell or compare potential differences. It works on the principle that the potential drop across a uniform wire is directly proportional to its length, provided the current is constant. By adjusting the length of the wire, you can find the point where the potential difference matches the EMF being measured. The potentiometer is highly accurate and does not draw current from the cell being tested. Next, let's see why it's preferred over a voltmeter. Potentiometer is preferred over a voltmeter for measuring EMF because it does not draw any current from the cell being measured. This ensures that the measurement is accurate and unaffected by the internal resistance of the cell. In contrast, a voltmeter draws a small current, which can lead to errors in the measured value. The potentiometer's high sensitivity and accuracy make it the instrument of choice in precise electrical measurements. Now, let's summarize what we've learned so far. You've covered a wide range of topics in current electricity, from the basic definition of electric current to the principles behind complex instruments like the potentiometer. Understanding drift velocity, mobility, Ohm's law, resistivity, and conductivity forms the foundation for analyzing electrical circuits. We also explored how resistors combine in series and parallel, and how Kirchhoff's laws help solve complex networks. Special circuits like the Wheatstone bridge and meter bridge allow for precise measurements. Let's reinforce these ideas with some practical examples. Let's apply what we've learned with a simple example. Suppose you have a wire with a known number density of electrons, a given cross-sectional area, and a measured drift velocity. Using the formula I equals N of A, you can calculate the current flowing through the wire. This practical application shows how microscopic properties translate into measurable quantities in real circuits. Next, we'll look at how to use Ohm's law to find resistance in a circuit. Suppose you know the voltage across a resistor and the current flowing through it. By rearranging Ohm's law, you can calculate the resistance as R equals VI. This simple calculation is fundamental in circuit analysis and helps in designing and troubleshooting electrical systems. Understanding how to apply Ohm's law in real situations is a key skill for anyone working with electronics. Next, let's see how to analyze circuits with resistors in series. Imagine a circuit with 3 resistors connected in series, 2 ohms, 4 ohms, and 6 ohms. The total resistance is simply the sum, 2 plus 4 plus 6 equals 12 ohms. This straightforward method makes it easy to analyze series circuits and predict how they will behave. Knowing how to combine resistances is essential for building and understanding more complex circuits. Next, let's try a parallel resistance example. Now, consider 3 resistors in parallel, 2 ohms, 4 ohms, and 6 ohms. The total resistance is found using the formula 1R total equals 1 2 plus 1 4 plus 1 6. Calculating this gives a total resistance of about 1 ohm. Parallel arrangements are useful when you want to decrease resistance and increase current capacity. Understanding these calculations is vital for practical circuit design. Next, let's solve a circuit using Kirchhoff's laws. Suppose you have a circuit with 2 loops and 3 resistors. By labeling the currents and applying Kirchhoff's current law at the junctions and Kirchhoff's voltage law around each loop, you can set up equations to solve for the unknown currents. This systematic approach is essential for analyzing complex circuits that can't be simplified into series or parallel. Next, let's see how the Wheatstone bridge is used in practice. A Wheatstone bridge, you can measure an unknown resistance by adjusting the known resistors until the galvanometer shows 0 current. Using the balance condition, you can calculate the unknown value accurately. This method is widely used in laboratories for precise resistance measurements. Understanding how to use the Wheatstone bridge is a valuable skill for experimental physics. Next, let's see how the meter bridge works in a real scenario. Using a meter bridge, you connect a known and an unknown resistor in the bridge arms and slide the jockey to find the balance point. By measuring the lengths on either side of the balance point, you can use the Wheatstone bridge formula to calculate the unknown resistance. This hands-on experiment is a staple in physics labs and demonstrates the practical application of theoretical concepts. Next, let's look at potentiometer measurements. The potentiometer, you can measure the EMF of a cell by connecting it in series with a long wire and a standard cell. By adjusting the length of the wire until the galvanometer reads 0, you can compare the EMF of the 2 cells. This method is highly accurate because no current is drawn from the cell being measured. Potentiometers are essential tools in electrical measurements. Next, let's discuss the importance of material selection in circuits. Selecting the right materials for electrical circuits is crucial for efficiency and safety. Conductors like copper and aluminum are chosen for their low resistivity and high conductivity, ensuring minimal energy loss. Insulators such as rubber and plastic are used to prevent unwanted current flow and protect users. The choice of materials also affects the durability and performance of devices. Understanding resistivity and conductivity helps engineers make informed decisions. Next, let's examine the effect of temperature on circuit performance. Temperature changes can significantly impact the performance of electrical circuits. As temperature rises, the resistivity of conductors increases, leading to higher energy losses and potential overheating. In semiconductors, increased temperature can improve conductivity, which is useful in devices like thermistors. Engineers must consider these effects when designing circuits for different environments to ensure reliability and safety. Next, let's discuss the role of circuit protection devices. Safeguard electrical circuits, various protection devices are used, such as fuses and circuit breakers. These devices interrupt the flow of current when it exceeds safe levels, preventing damage to components and reducing the risk of fire. Proper circuit protection is essential in both household and industrial settings. Understanding current, resistance, and the behavior of materials under different conditions helps in selecting the right protection devices. Next, let's look at the importance of grounding in electrical systems. Grounding is a critical safety measure in electrical systems. It provides a safe path for excess current to flow into the earth, protecting both people and equipment from electric shocks and damage. Proper grounding ensures that any fault currents are safely dissipated, reducing the risk of injury or fire. Understanding the principles of current flow and resistance is essential for designing effective grounding systems. Next, let's explore how current electricity is used in everyday devices. Current electricity powers countless devices in our daily lives, from smartphones and computers to household appliances and industrial machines. Understanding how current, resistance, and voltage interact helps us appreciate the design and function of these devices. Engineers use the principles we've discussed to create efficient, reliable, and safe products. Next, let's consider the environmental impact of electrical energy use. Generation and use of electrical energy have significant environmental impacts. Power plants that burn fossil fuels release greenhouse gases, while renewable sources like solar and wind are cleaner alternatives. Efficient use of electricity, through proper circuit design and material selection, helps reduce energy waste and environmental harm. Understanding current electricity is not just about theory, it's also about making responsible choices for our planet. Next, let's look at the future of electrical technology. Future of electricity lies in smarter, more efficient technologies. Advances in materials science are leading to better conductors and semiconductors, while innovations in circuit design are making devices more energy efficient. Smart grids, renewable energy integration, and electric vehicles are transforming how we generate, distribute, and use electricity. Staying informed about these trends is important for anyone interested in science and technology. Next, let's review some common misconceptions about current electricity. Many people believe that electrons move at the speed of light in a wire, but in reality, their drift velocity is much slower. Another misconception is that current is used up as it flows through a circuit, but current remains the same in a series circuit. Clarifying these misunderstandings helps build a solid foundation in electrical science. Next, let's discuss the importance of safety precautions when working with electricity. Working with electricity requires strict safety precautions. Always ensure circuits are de-energized before working on them, use insulated tools, and wear protective equipment. Understanding the principles of current, resistance, and voltage helps prevent accidents and injuries. Safety is paramount in both educational and professional settings. Next, let's look at how current electricity is taught in schools and colleges. Current electricity is a core topic in physics curricula worldwide. Teachers use demonstrations, experiments, and simulations to help students visualize concepts like current flow, resistance, and circuit behavior. Hands-on activities, such as building simple circuits or using a meter bridge, reinforce theoretical knowledge. Effective teaching ensures that students not only memorize formulas, but also understand the underlying principles. Next, let's explore careers related to electricity and electronics. Strong understanding of current electricity opens doors to careers in electrical engineering, electronics, renewable energy, and more. Professionals in these fields design, build, and maintain the systems that power our world. Whether working on power grids, consumer electronics, or innovative new technologies, knowledge of current electricity is essential. Next, let's look at some famous inventors and scientists who contributed to this field. Many great scientists have shaped our understanding of electricity. Georg Ohm formulated Ohm's law, Gustav Kirchhoff developed his circuit laws, and Charles Wheatstone invented the Wheatstone bridge. Their discoveries laid the groundwork for modern electrical science and technology. Learning about these pioneers inspires us to appreciate the history and progress in this field. Next, let's summarize the key takeaways from this chapter. In this chapter, we've explored the essential concepts of current electricity, from the movement of charge carriers to the laws and devices that govern circuit behavior. Understanding these principles is crucial for anyone studying physics, engineering, or working with electrical systems. Mastery of current, resistance, Ohm's law, and circuit analysis provides a strong foundation for further study and practical applications. Let's conclude with some final thoughts. Current electricity is more than just a topic in physics. It's a vital part of our everyday lives. From powering homes to enabling technological innovation, understanding how electricity works empowers us to use it safely and efficiently. Keep exploring, experimenting, and applying these concepts to real-world problems. Thank you for joining us on this journey through current electricity. Stay curious and keep learning. This concludes our comprehensive guide to current electricity. We hope you found the explanations, examples, and derivations helpful in deepening your understanding of this important subject. Remember, the principles you've learned here are the building blocks for more advanced topics in physics and engineering. Continue to practice, ask questions, and explore the wonders of electricity in the world around you.